Okay, this practical is dealing with pressure and temperature, and you've probably watched the theory lesson before you've done this. You'll do this practical, but just to recap on the ideas, if we had not that different to a practical on Boyle's law, if we had a container, but this time was sealed off and no motion happened here, and we had a certain pressure and temperature, each of these particles inside will be rushing around. And remember, the definition of temperature is the average kinetic energy per particle. So that's the definition for temperature. So if we have a higher temperature, then one of those has more kinetic energy, i.e. it's moving faster. And if it's moving faster, not only does it hit the wall faster, but also it makes more frequent collisions. So not only does it impart more momentum, but it's also more frequently doing it. So therefore, as the temperature increases, we'd imagine the pressure to be increasing and vice versa. In actual fact, we think it's proportional. We think that pressure is going to be proportional to temperature, or in other words, pressure is going to equal a constant multiplied by the temperature. So that's quite straightforward. However, it's probably worth saying that if the temperature is 0, then you have no kinetic energy of the particles, and therefore there is no pressure. However, at 0 degrees Celsius, particles are still moving. So the temperature must be in Kelvin. We're going to take temperature in Kelvin to appreciate this better. Or indeed, you can start your number line behind 0. So remember, if there's no temperature in terms of Kelvin, there is no pressure. Right, okay then, what are we going to do? Right, what's our independent variable, like we do with all of these experiments? Our independent variable is going to be what we're changing, and what we're changing is the temperature. We're controlling the temperature. What we're measuring, the dependent variable, is going to be the pressure. Because we're going to attach a pressure sensor to a computer that's going to tell us what the pressure is. Good, so very simply your table will look something like this. It will be temperature, and this time we will do it in degrees C, and there's a good reason why we're doing it degrees C. And then we'll take the pressure, and that's measured in kilopascals on the computers that we're using. So there is our table of results, always independent on the left, dependent on the right. And it's probably best that ideally we'd ask to be doing repeats and get an average, but once again, the pressure sensors themselves are very sensitive, and so therefore we're unlikely to get a good repeat. They have different 0 points. Okay, so let's just show the setup of how we're going to do this. I suppose the first question is, how are we going to alter the temperature? You can probably hear behind me that's a kettle boiling, and that gives us a hint on what's going to happen. So here is my setup. I have my vessel, which is that there. It's sealed off at the end, and then this end is leading us to the computer. So I have my pressure sensor, my gas pressure sensor, heading off to the computer. There it is. The question was, how are we going to control the temperature? A water bath is the best way to control the temperature. So I'll have my vessel, you can see this glass. We're going to have my vessel inside a container, to fill it with water, and I'm going to test the temperature with another sensor. Good, there is my setup. First instance. Right, let me bring in the computer and show you the readouts. The computer here, if I bring those into view a little bit more easily, will give us a temperature and a pressure. And here with vessels. So I think this makes sense to start with in the first instance, in that the temperature is room temperature, a balmy 21 degrees, and the pressure is 106.14. Let me just going to take the pressure off the top just to make sure I've hit the right temperature, atmospheric temperature, pressure, sorry. So I've equalized that. Now, what I will want to do to start with is I'm going to want to make that very hot. And so therefore, I'm going to add some boiling water to this, and let's just see what happens as I heat that up. Okay, there we go. You can see it's getting very hot. And the pressure is subsequently increasing. Well, should we say it had a huge spike, but the pressure is balancing out. You must make sure to stir it because we don't have any hot pockets affecting our results. You can see there, temperature starting to drop. Okay, so what we're going to do is we're going to measure our temperature at certain points, whichever points you want those to be, because it's really hard to control temperature, especially in a water bath. But nonetheless, take a few points, say every 10 degrees. And then, what we will then do is we will start adding water to, well, I'm going to get it cooler quickly as an ice cube for you. And we're going to then bring the temperature down. You can see it coming down. And you can also see the pressure decreasing simultaneously. Pressure's decreasing as the temperature's decreasing. And we'll continue that process all the way along. I'm going to use ice to speed this process along. But I'm also going to use ice because I really want to get the temperature down here, down to 0 preferably. So that's the setup. That's the technique. I don't think it's particularly difficult. And I've got a series of results in the link below, which you can download, and then I'll explain how to use them in a minute. Okay, here are the results. I managed to get it down to -15 by throwing some salt in there as well. Once I'd got it down to 0-ish with lots of ice, I threw in some salt just to see what would happen and see whether it dove down any further. Managed to get it to -15, and there are the series of results. Now, when it comes to plotting a graph of these results, what I want is, I would like us to plot pressure in kilopascals against the temperature in degrees C. And what we'll probably see if you did that initially is that the results do something like that. The wonderful part of this experiment is if I continue this axis back, then what you'll notice is that this continues to drop back, and you'll probably have to extrapolate. That's the furthest result I've got, about there. So therefore, if you extrapolate, so I've got a series of results like this. If you extrapolate the line all the way back to the axis, then what's happening is you find a point at which the pressure is 0. And we said if the pressure is 0, then the temperature in terms of Kelvin must equal 0, because Kelvin, remember, is how fast the particles are moving. In other words, this should be coming out to be something like 273 degrees C, absolute 0. So plot them. I mean, it does have what's going to affect the results greatly is whether the pressure was zeroed correctly, because if the pressure was measuring just slightly higher, if there was a systematic error, then suddenly our systematic error would kick absolute 0 way beyond. Similarly, if it was below by a systematic error, then it would kick our results grossly wrong. But I mean, first and foremost, we know the gradient is dead on with these meters. Okay, so that means, to come back to the original bit, that temperature and pressure are directly proportional, vertically constant. But the wonder of this is that you might be able to get an approximation for absolute C. The results are in the link below.